is going to be by Erica, and Erica is going to talk about the role of the actinides compared to lanthanides and neutron star merger dynamical ejecta. It's a nice work. It's I've been reading about this on her new paper on arXiv, but she's going to present this for all 50. So please start, Erica.
Okay, thank you. Thank you for the introduction, and thank you everyone for tuning in on a Friday. As Mohammed said, I'm excited to talk about some new progress we have made towards understanding actinide productions using both observation and theory, particularly in neutron star mergers. So before I talk about anything, this is a JINA talk, so I have to talk about the R process. Just as a reminder, about half the elements heavier than iron in the solar system were made by the rapid-neutron-capture process. The actinides, thorium and uranium up here, can only be made by rapid neutron capture, since slow neutron capture cannot cross this gap between bismuth and thorium. So in the R process, the network starts with some seed distribution of nuclei. Then those nuclei capture neutrons, in this case, very close to the neutron drip line. Then they reach about a maximum mass, and when the neutron flux falls off, they all beta decay back to stability. As you can see in this particular simulation, we end up with a lot of material in the actinide region, which will eventually decay into thorium and uranium. One of the major questions is, of course, where in the universe can the R process occur? Traditional core collapse supernovae have been all but ruled out, but exotic types of supernovae like magneto-hydrodynamic jet-driven supernovae, which I know nothing about, may still be R process candidates. Another site that has gained even more popularity since the gravitational wave event last year, and also the topic of my talk, are neutron star mergers. But there could be some other astrophysical site that the universe just hasn't revealed to us yet, or that we haven't thought about. One way we can learn about the R process and its astrophysical site is by looking at signatures that the R process imprints on the universe through R2 stars. Okay, what is an R2 star? First, it is metal poor. This is a solar spectrum inferred from the sky. I took this image, it comes straight off the telescope, there's very little processing. And notice all of these little black vertical lines. Each of those lines corresponds to an atomic transition of an element in the sun's photosphere. Obviously, there are a lot of them. The sun is quite metal rich. Compared to a metal poor star in the same region, I hope it's clear that this, you can immediately tell there are much fewer of these transitions, or they are much weaker, can't even see them. This particular star is a metallicity of -3, which means it has about 1/1000th of the iron that the sun has. Secondly, and more importantly, an R2 star is enhanced in R process elements. The solar system R process pattern is in blue here, and the abundances for this particular R2 star are in the black points. And this is a typical R2 star. The R2 stars have this elemental pattern that nearly duplicates what we observe in the solar system. On top of that, compared to their iron content, R2 stars have more than 10 times as much R process material as the solar system. So they're very enhanced in these R process elements. Why are R2 stars interesting? Why are they worthy of being studied? Their metal poor nature suggests that little chemical enrichment took place before these stars were made. That could either indicate that these stars are very old, or they were made out of a gas that just had not been enriched by many nucleosynthetic events. Their enhanced quality indicates that some strong R process event or events occurred before these stars were made to enrich the gas from which they were created. So these R2 stars are nearly pure R process patterns from one to a few R process events, unlike the sun, which has a lot of pollution in there. So I'd like to advertise the R Process Alliance. This is a multi-institutional effort with the main goal of understanding the R process. These are just the core members, and I'd like to point out that most are also JINA members. So to understand the R process Alliance has this whole plan about how we are going to learn about the R process more. The first few phases of that are through observation. And through those observations, one of our goals is to identify 75 new R2 stars. Before we started our observational program a few years ago, there were only 25 known R2 stars. These are very rare. So we want to increase that number to a nice, round, statistically significant 100 total R2 stars. Through this huge undertaking, the R Process Alliance has already observed about 1,250 metal-poor stars. We expect only 3 to 5% of metal-poor stars will be R2. So it's necessary to observe such a large number of metal-poor stars to get to our goal of 75 new R2 stars. The analysis is very slow, so we have only analyzed about 350 so far. But of those 350, we've identified 17 new R2 stars. Remember, as of a few years ago, we only knew of 25. So we are close to doubling that number already. And it's only been a few years since we started these observations. How we identify these R2 stars is necessarily through high-resolution spectroscopy. The R process signatures we look for do not appear with low-resolution spectra, so we need to take high resolution. It takes about, on average, maybe 30 minutes on a 2.5 meter telescope in order to obtain each of these spectra. We look for mainly 3 elements to characterize our process enhancement in the stars we observe. Strontium, which is this line on the left, barium, and europium. Then we use the relative abundances of those elements to classify whether the stars have our process enhancement. In particular, europium is used to classify R2 stars, since europium is primarily made through the R process, unlike barium, which can also be made heavily through the S process. Notice that this star, which turns out to be an R2 star, does have this huge europium feature. This star, an R1 star, is just kind of enhanced. It's not as enhanced as an R2 star, and you can tell by its europium feature. It's not as strong as in the R2. So we have to do this for every star in our sample in order to produce plots like these. This is a plot from one of the R Process Alliance pilot papers, and it shows the europium abundance as a function of metallicity. The solar level, what would be a typical solar value, is at 0 here. And the R2 stars we are looking for are at the upper end of this distribution. So maybe it's easy to tell there are very few and they are very enriched compared to other stars of their metallicity. So we've had many publications already as either a direct or indirect result of this observational effort. I'm sure I missed a few on this list. And I want to focus on 2 in particular that I was involved in. One of the early successes we had was finding an R2 star with a very catchy name that had an observable uranium feature. Before this star, there were only, I think, about 4 stars with uranium measured in their photospheres. And that's because uranium is very hard to measure. In this spectrum, you could probably barely see it. It's just this little dimple on the edge of this very large iron absorption feature, but it is there. This is a very high resolution spectrum, so this is not noise. Then we had another success recently, back in January. We observed this star, we found thorium and uranium, but this star is special. Maybe you can tell this uranium feature is much stronger compared to this other star. And that's because this star turned out to be an actinide-boost star. Now, what is an actinide-boost? It is an R process enhanced star that shows an extra enhancement of the actinides. The rest of the R process pattern looks like every other R2 star. It's a very typical R process pattern. And the actinides are much greater than what's in the solar system. CS31082-001 is the canonical actinide-boost star, and it's even more enhanced than that one. Actinides in stars allow for some fun and interesting physics. Thorium and uranium, these isotopes, are radioactive on very long timescales, billions of years. So we can apply radioactive decay dating to estimate the age of our process material in stars that have actinides. The only things we need are the measured abundance ratios, so these come from the observations, and some estimate of the initial production ratios, what the star was born with. Since we don't know that, those production ratios necessarily have to be from simulations. If the production ratios are a good estimate for what the star began with, then all three of these ages should agree. The material is only so old. It should all be one age. As I said before, uranium is very difficult to measure in a star, but it's very useful to have because you can use these other two equations instead of just relying on one, and that acts as a check to make sure that the age is correct and the production ratios are correct. And you'll see what happens with just thorium. So let's apply just that first age equation to stars with a particular thorium to europium ratio, which is right here. And the ages we get are on the right. This should be a little concerning. One of these stars is older than the age of the universe, and a handful of these have negative ages. They have yet to be born. These are the actinide-boost stars. This other star I labeled here, that's that first uranium star that I showed. It's not enhanced. It has kind of a typical amount of actinides. But this is that very actinide-boost star that we found. So what's going on? Why do the actinide-boost stars appear young? Young is an understatement. It goes back to these production ratios. Our process production ratios that are typically applied in the literature give low amounts of thorium. So if you start with a low amount, you end up with a high amount. That implies radioactive decay that is backwards in time, hence negative ages. To solve this problem, we need an R process that produces more actinides, that produces a lot of thorium to account for the actinide boost. So those previous R process simulations that predict those negative ages are mostly from neutrino-driven wind R process simulations and waiting point calculations. But what if we use production ratios from a neutron star merger R process? Can neutron star mergers make more actinides? Compared to a traditional core collapse supernova, neutron star mergers are predicted to be more neutron rich, which may encourage more actinide production by allowing material to get further up in the network. Neutron star merger conditions also allow fission. So notice in this movie that material will get to about the n equals 184 and about n equals 200, but really no further. At these masses, neutrons are more likely to induce fission than to capture, and neutron-induced fission terminates the R process in mass. That's why it doesn't get any farther. Those fission products deposit near the second R process peak. And if the conditions are neutron-rich enough, those fission products can themselves participate in the R process, get all the way up to around n equals 184, and then fission. When that happens, that's known as fission cycling. And in very, very neutron-rich environments, multiple fission cycles can occur in the R process. So next we will examine the onset of fission cycling and actinide production as a function of neutron richness. Can we turn a knob to change the neutron richness and then get different amounts of thorium and hopefully describe the actinide boost? To investigate this, we use PRISM. It's an R process network solver written by Trevor Sprouse and Matt Mumpower. PRISM allows for complete flexibility of the nuclear and astrophysical inputs. Each full R process calculation takes on the order of minutes on my laptop, which means we can perform many calculations very quickly. For this actinide boost question, we choose a low entropy neutron star merger tidal ejecta trajectory and vary the initial electron fraction between about 0 and 0.25. I'll be talking about YE a lot, so this is just a reminder for what YE is. It essentially measures the fraction of nucleons that are protons. So just remember that a lower YE means more neutrons, and a higher YE means more protons. So we ran 50 full R-process calculations, changing that initial YE between 0.005 and 0.25. Each of our calculations we run to 1 gigayear. So all the abundance patterns I'll be showing are at 1 billion years. Okay, so here are some final abundance patterns. At the highest YE in our simulations at 0.25, we can make the second R process peak, but nothing really beyond that. If we decrease the YE, we're starting to get lanthanides, we're starting to get the rare earths. Decreasing the YE further, we're finally starting to get that third R process peak. And then if I just play this and keep lowering the YE, the actinides eventually come in. But as the YE gets lower, we get more actinides, which is great. We are producing a lot of actinides, a lot of thorium. That's what we wanted, because we want to describe stars that have lots of thorium and uranium. This plot is just a summary of how those europium, thorium, and uranium abundances vary as a function of YE. Again, neutrons are increasing, going to the right. So starting from the highest YE, we're starting to get the lanthanides. Decreasing the YE further, the actinides start growing in. And then decreasing the YE further still, actinides decrease. What's happening here is that those extra neutrons are moving the bulk material from the actinide region up to a region where they can fission by neutron-induced fission. And those fission products deposit near the second peak and can capture up to europium. And we see this corresponding increase of europium because fission products are put into that area. We keep increasing the neutron richness. Now those products move up to the actinides, so our actinides start increasing again. And then further increasing the neutron richness, they go down because the fission is happening again. And this can happen several times at the very highest YE conditions. Or sorry, very highest neutron conditions. Let's take a step back and look at these age equations again. We're going to use the observations of that actinide boost star, that very, very high actinide boost, and the production ratios we will take from these simulations. I'm going to choose a YE around here, 0.035, because for this tidal, neutron star merger tidal trajectory, that is the suggested YE, is this very low YE. So let's just look at that one first. So picking those production ratios at that low YE, these are the ages we get for the actinide boost star. Here are those low literature production ratios from neutrino-driven winds and leading point calculations. Again, those predicted negative ages. Some of them were negative, which we saw earlier. But now our simulations are predicting thorium that is so high, it would take about 50 billion years to decay to what we actually observe. And notice that the three ages don't agree, which is an indication that the production ratios are wrong. If 50 billion years wasn't an indication, the fact that they don't all agree to the same age should tell us that maybe our production ratios are wrong. So what happened? Maybe the YE is too low. We chose this very low YE, but there's this incredible variation of the actinides at slightly higher YE. So let's look at those three ages across this whole range of YE. And that's what this is. This plot shows the ages of this actinide-boost star across the whole YE range that we ran, using those 3 production ratios from those 3 age equations. What we want, what would be a successful description of the elements that this actinide-boost star would have started with, is for all 3 ages to agree. That at that point, that would be a good description. That point only happens at 1 YE in particular. Anything below a YE of 0.17 will always overproduce the actinides, some in crazy amounts. This is saying 75 billion years for the age of that star. Maybe this is a nuclear physics problem. These simulations were run using the FRDM 2012 mass model. So we tried it with a different mass model. We tried it with Duflo-Zucker. PRISM does allow this capability of switching out the nuclear input to update the lifetimes and reaction rates to be consistent with the mass model. So that's what we did, and ran all the calculations again. These ages are better, but the actinides are still overproduced, way overproduced past a certain point. We can continue to look for nuclear physics solutions to fix the ages, or we can turn to astrophysics, which that's what I'm going to do. This star is currently the most actinide-enhanced R2 star known. We don't observe the actinides any higher, not yet at least. So we need a way of diluting the actinides in our simulations, but keeping the lanthanides, then that rare earth region, so that the thorium to europium ratio is nice and low for our age equation. So let's take a few more steps back and just talk about neutron star merger components. In principle, we can have ejecta from multiple environments within the neutron star merger, and those environments may have different astrophysical parameters, such as YE. There might be our process somewhere else besides that dynamical ejecta of the neutron star merger. For example, the accretion disk wind that forms around the merger remnant typically has a higher YE. In this particular work, they found a YE between maybe about 0.1 and 0.3. So we developed an actinide dilution method by constructing a range, a distribution of YE. We chose a distribution of YE based on what we found in literature for the tidal and wind ejecta. Since we have all these calculations run at different YEs, we used our higher YE results as a stand-in for the wind component. And then we also chose a mass ratio of ejecta type from the literature as well. So we assumed that the mass of the wind, the wind ejects 3 times as much mass as the dynamical ejecta. These are all just literature values, some inspired by the gravitational wave event and associated kilonova last year. So now we've constructed this distribution of YE, and we can apply the final abundances that we ran for each of those YEs. We can apply that distribution to those abundances to get a final combined abundance. So using that mass distribution motivated by literature, we get the final combined abundance pattern in red here. Each of those individual blue and green lines, that's just running one of those YE trajectories. And this is promising, very promising. We did indeed dilute the actinides. In one of our worst offending cases, the actinides are all the way up here, and we've taken it down to a level that approaches observed points. These white points are for that actinide-boost star that we're considering. And we kept the lanthanides. The lanthanides look great. It looks like a typical R process pattern. So we were able to take down the actinides, but keep the lanthanides. But what does this do for the ages? We went through this whole dilution process in order to make the ages at least be within physical bounds. And we get the ages in red. We applied our actinide dilution method to find an age for the star. The ages we found are much more realistic than the previous result from just one very low YE trajectory. 15 billion years is, I think, much more successful than 50. Still a little bit outside the age of the universe, but better, we're getting there. The mass distribution, again, we just chose inspired by literature, so it could be that a different choice of mass distribution or different nuclear physics could make these ages agree perfectly. But we at least need some type of dilution scenario if we want neutron star mergers to be the source of the actinide boost. So in conclusion, the R-Process Alliance is searching for more R2 stars, so we have more observational data to study. During our survey, we've had many successes already, including identifying the most actinide-enhanced R2 star currently known, which brings up the question of how the actinides are overproduced in nature. We investigated whether neutron star mergers can produce this actinide boost and found that very neutron-rich dynamical ejecta not only produces the actinides, but produces them in amounts that are much too high compared to current observations. Neutron star mergers could still be a source of the actinide boost if we account for the R process taking place in some higher YE environments as well. For example, perhaps through the neutron star merger accretion disk wind. And thank you, I'll stop there.
Awesome, that was an excellent talk. Let's see, if anybody has questions, please raise your hand or just simply turn on your mic. Yep, please.
Yeah, great talk, Erica. One quick question to start. What is like the error bars around some of the predictions from the models that you have? So I see a lot of points, but I have no sort of sense of what are the built-in errors for some of these methods.
Okay, so do you mean, let me go back.
So for instance, even if you're looking at the ratios for like uranium to thorium and it just actually your final plot of getting them to agree with like sort of the YE measurements, like what is like the error bars on those curves or the final points?
Okay, I'm sorry about this. I'm not.
It's okay.
Okay.
That's great.
Okay, this I'm really sorry about this. It'll calm down eventually. Okay, yes, that's a very good question. Let me go back to, let's see if I can actually just get to the slide from here. Oh, almost perfect. Nope. I'm really sorry about this. Okay, right. Yes. Observationally, those abundances have quite a large uncertainty, as you know, which translates to an uncertainty on the age about maybe 2 to 3 billion years. So that uncertainty is quite large. From
so
sorry?
So I was to say, yeah, so from the theory side, so for instance, you have the initial...
Well, from the theory side, it depends on how you want to define an uncertainty, because there are huge uncertainties in the mass model. There are uncertainties in neutron capture rates and beta decay rates. So yes, if I included all of that, those curves that I showed would be quite broad.
Okay.
Yes. So they would be quite broad because there are a lot of uncertainties. It is highly theoretical.
Okay. It's just good to know. How can, if you're adjusting things to get them to work, of course, if there's huge broad, error bars and ellipses, then, it sort of calls into question, like, what specific thing do you think you should focus on in terms of, reducing the errors?
Yes. It's almost what I had. Yes, well, I will say, let's go back to my final slide. We did run this for DZ. We tried the ages. And DZ it started about up here. So with that mass model, the actinides are still overproduced. So maybe that could give you some type of error bar on that, if that makes sense.
Sure, thank you.
Yeah, that's just the mass model too.
I guess we have a question from Chuck Horowitz.
Yeah, can you hear me?
Yes.
The question is, why do you believe the YEs that come from the individual components of the ejecta in the neutron star merger simulations?
Why do I believe the YEs? I'm sorry, what exactly do you mean by that? I just want to...
Presumably there's a large theoretical uncertainty.
Yes.
When you change the average YE by mixing components together.
Mm-hmm.
But if there's uncertainty in the YEs of the individual components,
oh, sure,
the mixture you need may be very different.
Oh, yeah, it could. Yeah, it could be completely different. This was just one example we chose. Yeah, it could be much different. And this is a combination of literature anyway. It's not just one reference that we're choosing. These are 3 different things that we're piecing together. So yes, maybe this isn't an accurate description of the ejecta of a neutron star merger, but it looks like we can't, if we want neutron star mergers to be the source of the actinide boost, there has to be some way of taking those actinides down, because with just one very neutron-rich environment, it overproduces the actinides in our simulations. So yes, it could be a different distribution entirely. This is just a test that we did.
I mean, to follow up on
related
this.
question. Sorry, can I ask a related question? This is Sanjay. And related question is, to fit the light curves, people who are modeling the light curves, the kilonova light curves, had to pick some mix of YE. Is that mix of YE, did you guys try it, and does it provide a better fit or a worse fit?
We didn't try it for this work. That is all I will say. It is something we are thinking about right now. So yes, that is the natural way to go from this. And yes, we are making that connection. We are just not ready to do that in this paper.
So something new is coming.
Yes, something new is coming.
So to follow up on this, would it be possible to actually run a different now you're choosing like 2 different YEs and then the mass ratio, and then you fit the data better than before. Now, could you use a PDF for each one of them, and then also a PDF of mixture, and then run it through, and then come up with like a PDF of what is the 68% like percentile of plausible mix? Or do you need, I mean, 2, maybe there is 3 components, and then maybe there is a width to each one of them. I mean, 0.22 is, no, it has an error bar, definitely. So to run it through and then get like a at least 1 sigma, 2 sigma, 3 sigma estimate of what is the preferred mixture, what are the 2 components, the median value. I mean, have you done that?
Well, just to clarify,
the 15 gigayear to 13 gigayear. Maybe that makes it a bit better.
Yeah, just to clarify, this is not just, we didn't choose just one YE at 0.16 and one at 0.22. These are 2 distributions. So we're mixing a bunch of components that just happen to be centered at 0.16 and 0.22. But yes, again, we are thinking about that, and yes, all I will say is yes, you are right. This is just an example distribution. We could, in principle, test any distribution, come up with our own. Yeah, that's all I'm going to say about that. Just
so
keep your eye on the
question. We have a question from Jinmi. She cannot turn on the phone. So the question is, could NLTE and 3D effect influence on the observed data of the R process elements? If then, how much? And then on the interpretation and age.
Yes. Oh, yes, of course. Let me see if I can go back to that plot. This might be painful. Yeah, so that, okay. Wow, well, I don't want to go all the way back, sorry. Yes, non-LTE abundances, of course, that'll affect mostly the model atmosphere that fits the star. And before we measure any of these abundances, we have to get the atmospheric parameters for the star. And non-LTE there are different numbers that come out of that. It depends on the temperature and the metallicity, how big that effect is. And I don't know those numbers off the top of my head, probably between 0.2 and 0.3 dex. Which would be, in this case, I have a 0.2 error bar on uranium, so it could be that or greater. And then an uncertainty of 0.2 on the abundance translates to about that 2 or 3 billion years in the age. So yes, that is an uncertainty, is whether the atmosphere has been done correctly.
Yep, okay. Anyone else? I mean, I have a question on whether this ratio of R2 metal poor stars to metal poor stars, like the fraction of all the metal poor stars that are R2, and also those that are R1. I mean, how robust is the fraction? I mean, when you say, for example, 10% or a few percent, I mean, what is the error bar on that number?
Okay. Well, now they're not displaying at all. Okay. I'll let me go back to that slide. Yes, that's something that we are wondering, and something we're trying to answer through all of these observations. Because that 3 to 5%, that was established, I don't remember when. I think around the 90s. Oh, I don't remember. But that was for a small sample, and we're finding that this is 17 R2 stars out of 350. That matches with that 3 to 5%. I think that's about on the 5% end. So yes, it does seem like our observations are matching that expected rate. Does that answer your question?
Yes, so there's an expected rate of 5%. Where does this expectation come from?
All right. It's just empirical. It's just from doing observations. Yeah. Yeah, just from looking at these points, it's not a lot. These stars are rare.
And is there any observational bias that we need to consider here, or is it just, I mean, when you say like 5%, I mean, how should I take it? Is it, I mean, this is all the metal poor stars that have been observed with high resolution spectroscopy?
Yes.
Okay, so from that sample, this is a random sample, and then you see 5%.
They're all bright. They have to be bright so that we can do these high resolution spectra somewhat quickly. And they're all giant stars, which contributes to them being bright. So maybe that is some type of bias, but our selection is only targeting metal poor stars that are bright. So there could be some bias in there from that, but we're not making any cutoffs, or there isn't really a bias that we are controlling besides just the brightness and the metallicity.
Okay, cool.
We have a question.
Okay.
Yeah, well, actually two, but so they're pretty naive. First question is, how sensitive are the calculations to your initial seed distribution, and how sensitive are the calculations to how long you run the R process?
To the initial seed distribution, for this, oh, okay, I know I've run these, not extremely. It does change those curves that I showed with thorium, europium, and uranium. It does move that around a little bit. Because when I first did this test, I just started with just protons and just neutrons. And I still saw those nice curves, but it was a little different from these calculations. In these, I started with seed distribution in nuclear statistical equilibrium. So it's not too sensitive, but there is a little bit of sensitivity in there. We still see those nice fission cycles. And I'm sorry, can you repeat the second question?
How sensitive is it to how long you run the R process?
Right. This is interesting. I run my calculations out to 1 billion years, which seems like a long time, but that thorium abundance, that thorium-232, is still being fed by alpha decays of longer-lived isotopes. So I have to start that late because that's when thorium really starts its radioactive decay. It's not being fed anymore. So if I start earlier than about 1 billion years, those initial production ratios will be completely off because the thorium will be lower. It's still being fed by uranium and plutonium. If I start it later, then it's just a matter of that age offset. Starting later than 1 billion years, it's just doing that decay. So it would just be an offset in the age.
Okay.
I have a question, if that's okay. So this is Zach from Ohio. That was a great talk.
Thank you.
The question that I have is, so my understanding of your dilution method is that you weighted the results from different simulations that you ran, and the only difference between the simulations was the electron fraction that you chose. But would the trajectories not themselves be very different, like the density and temperature evolution versus time? And are you looking into that?
Yes. Yes, you're right. We chose just our higher YE simulations as a stand-in for the wind, but at its heart, those trajectories came from a tidal ejecta. So yes, you are right. Technically, we should be using a wind trajectory for the wind component. And again, yes, we are looking into this. I can tell you that when you vary the YE, that same variation happens. It's just because the temperature and the density are a little different. Those curves just kind of shift over at a different YE, but the same pattern happens. But yes, you are right.
Okay, thanks.
Yeah.
Is there any more questions? I have one more question to ask, but if there's any one. So there is this recent paper by Dan Siegel and Jennifer Barnes that they advocate the collapsar model. I mean, how is this related to what you're proposing to account for the actinide booster stars?
I saw it. I haven't read it yet.
Okay.
So I don't know. I'm sorry. I can't answer that question, but I saw it and I was intrigued by it.
Okay, fair enough.
I'm sorry.
So they have a question. Have you look at the actinide on R1 stars?
The driven wind from the accretion disk.
Wait, I'm sorry. There's some. What was the question?
So we have a question again. The question is: have you looked at the actinides on R1 stars? If then, could any of them show high actinides?
Yes, R1 stars. Maybe I should have gone to. Okay, R1 stars do show actinide boost. Yeah, there are a few actinide boost R1 stars. We have not specifically looked at R1s because the R process patterns for the R1 stars, they look pretty much exactly like the R2 stars. They are just at a lower level. So you just take that pattern and you drop it down by a little bit. So we don't know, or we don't expect that the actinide boost will behave any differently because those thorium to europium ratios for R1 stars are the same as R2 stars.
Okay. Any more questions? Well, that was an excellent talk. I really enjoyed it myself.
Thank you very much.
And well, let's thank Erica again. We'll have a nice talk in a month, I guess, from now. And hope to see you all again soon.